And we can see also that the same dopant level concentrations, they would not work for germanium or for gallium arsenide. Today the topic is doping and crystals. So there will be in fact two parts. First about the doping and the second about crystals. Regarding doping of semiconductors, the topics that I would like to discuss today is controlling the resistivity, donor and acceptor dopant elements, so that regarding the dopings we know which elements can be used for what type of N-type and P-type doping. The Fermi energy, how does it change when we have extrinsic semiconductor? I add the word extrinsic here because I'm not sure I use that very often, but also this expression, but usually we refer to semiconductors that are doped to extrinsic, on the contrary to intrinsic semiconductor. Doping levels, what is the minimum and the maximum doping level? Charge carrier concentration versus temperature. We touched the topic in the previous parts. And now when we have clearly covered what is the doping, we will look once again on how the charge carrier concentration changes with the temperature. And then what is related to that, the minimum and the maximum operating temperature for semiconductor material. Mostly we will focus on silicon, but again I will try to give some examples what other materials are used, especially for some extreme temperature applications. So if we speak about semiconductors, and very often for digital circuit is that we want to make a switch that it's either switched on or switched off. And how we can control the resistivity. So it's not a mechanical switch, but semiconductor. So we have to do something to control it. And let's remember from the previous part, conductivity. What influences the conductivity? So the conductivity is the sum of those two parts related to two types of charge carriers, the electron and the hole, and their mobility. So we have the mobility and the charge carrier concentration. So if we want to have a switch that is switched on, then we need to have a concentration of those charge carriers that is very high, and we are going to be able to control it in a MOSFET with electric field. But also what we already know from the previous lecture is that with the temperature, for example, we can also see the changes in the conductivity. So when we make MOSFET transistor, it can be either P-type or N-type. So the dominant charge carrier is, the majority charge carrier is either hole or electron. And we can change the concentration of those charge carriers as the initial concentration by adding doping to the semiconductor. And this is what I would like to focus now on. So maybe you remember this plot. We have the charge carrier concentration of the intrinsic semiconductor as a function of temperature. So the low temperature, 0 Kelvin, is at the right-hand side, and as we go closer to the left side, we see that the temperature is increasing, so 1 over the temperature is decreasing, and the concentration is increasing. And we had this example for 3 materials, germanium, silicon, and gallium arsenide. And if you remember, we saw that because of the band gap that is different in those 3 materials, also the thermal generation of charge carriers is not identical, and that's what's the difference. That's what makes the difference in the charge carrier concentration. Now, if we would like to add doping to, in particular, I will talk about germanium and silicon because these are simple, not like gallium arsenide compound semiconductor, but simple one-element crystals. And if we want to add doping, we will be considering either the column on the left-hand side with one less valence electron, or the one on the right-hand side with one more valence electron. And this will define whether we have p-type or n-type doping, one more electron or one less. And this boron, phosphorus, and arsenic are those that are most often used. And when we have a look on the model of those atoms, so it's just a very simple representation, we can see that silicon has 4 valence electrons, and then germanium as well. And then this is what makes the difference in the periodic table, the valence shell with the valence electrons, which is 3 for boron, and for phosphorus and arsenic, there are 5 of them. If we make a drawing with a model of the crystal of the semiconductor, we can draw it like that. We have the covalent bonding between every atom makes covalent bonding with the neighbors. With each neighbor, it has one covalent bonding, and that means if it has the silicon atom has 4 valence electron, it can make the maximum of 4 valence. More is anyway not possible. We can make covalent bonding with 4 neighbors, and that makes it having 8 shared electrons. And this is what makes a very stable structure. So the crystals, thanks to that, are very hard structures. And what we do when doping is replacing one atom in this structure with a different atom. So we can draw also this lattice model like that, and we can imagine that all of them are silicon atoms, and we will be replacing them with either boron or phosphorus or arsenic. So let's have a look at what happens when we do that. So in this case, we are talking about n-type semiconductor doping. We will have arsenic, which is added to the silicon lattice, and arsenic has 5 valence electrons. So in addition to the 4 that we need for covalent bonding, there is one more. And this one more electron, we need very little energy to give to this electron, so which happens normally with thermal energy, that the electron will become a free electron and can be used as a charge carrier. So like that, we will have an additional electron. But of course, the charge neutrality has to be fulfilled, so the ion, the arsenic ion, stays positively charged. And this is also what the positively charged ion is what causes later a scattering of charge carriers that are moving through the lattice. So you will see later we will come to the topic of the minimum maximum doping levels, and something that happens when we have very high doping level concentration is that these scattering effects become more significant more and more, and at some point they are also causing degradation of some charge transport properties of semiconductor. So in addition to arsenic, we can use also some other atoms which also will have 5 valence electrons. And like that, we have the n-type semiconductor. So n-type MOSFET, for n-type MOSFET, actually for p-type MOSFETs, we, in both cases, we have n-type and p-type doping because we will have different doping on the drain and source, and different at the bulk is just the difference also in the charge carrier concentration. So the other type of doping is doping that is achieved with the group 3 of elements, and this will be, for example, boron. It has 1 electron less in the valence shell. So if we place the boron atom in the silicon lattice, then it will form covalent bonding with 4 neighbors, but in fact, there is one missing electron, and this missing electron will be filled by electrons from, so we can see it as a possibility for the charge transport, because this missing electron can move from one atom to another, and the electron from the neighboring atom, by getting some additional energy, it can move to fill in this hole, leaving the hole behind in a different location. And this propagation of the hole, it will be also something that we see as the charge transport, and we see it as a charge carrier. It just has different properties. It has different mobility than electron. So like that, we have the p-type semiconductor. We can use also other elements from group 3, like for example, another that it's very often used in semiconductor manufacturing is aluminum. Now, in the previous plot, which we were looking at how the charge carrier concentration changes as a function of temperature, we were seeing just this Arrhenius plot, which in logarithmic scale it's a straight line. If we can focus for a moment on the numbers that we have there, so in silicon at room temperature we will have 5 times 10 to the power of 22 atoms per cubic centimeters. Sorry, that's the number of atoms in silicon per cubic centimeter, which is not related to the temperature. So that's something that is fixed by the lattice. And so from this number of atoms result in the charge carrier concentration that is temperature dependent. And the typical values of doping that we have in semiconductors, there will be something like 10 to the power of 13 to 10 to the power of 18. Of course, physically, it's not possible to have, I mean, we would have some very compressed material, which would not be crystal. So maintaining the crystal structure, we can replace the atoms reaching the concentration in silicon, 10 to the power of 18. And there are some, so there are the two extremes. Probably we can do better than 10 to the powers of 13. We can probably make the smaller concentration. But I would like to focus here what limits the bottom, the lower and the upper concentration of the dopant atoms. One concern that we have that we can maybe visualize looking at this model is at this model, and also the 2 atoms that we see in the top right corner, with the different atomic number, then also different number of electrons, the size of the atom will be different, depending. So it's silicon or the dopant atom boron or maybe aluminum. The dopant atom can be smaller or larger than silicon, and that already creates some tensions in the silicon structure. So if we have very large numbers of dopant concentration, also that can change to some extent the structure of the silicon. Maybe before going to the details of this extreme charge carrier concentration, I will come back to that. We see here a slide with energy band model, where we have an intrinsic semiconductor and an N-type and P-type semiconductor. So in one slide, we have the intrinsic and the extrinsic semiconductors of both types, N and P-type. In both cases, all 3 cases, let's say we have the same type of semiconductor, and let's think, for example, of silicon, but it doesn't have to be silicon. We have charge carrier generation of the intrinsic semiconductor, but this same thermal generation happens in the extrinsic, and this causes the intrinsic charge carrier concentration. Now, if we have at room temperature, we know that there will be already 10 to the power of, I think it was 15 charge carriers per cubic centimeter. If we have just something much smaller concentration of dopant atoms, then it will be invisible. We will not. It will disappear in the crowd. So we need to have something comparably large in the magnitude in terms of charge carrier concentration to see the effect of doping. So what we can hear is that for n-type semiconductor, the charge carrier concentration is the intrinsic charge carrier concentration plus the dopant atom concentration. And usually our goal is to have the charge carrier concentration due to doping, which is much higher than the intrinsic charge carrier concentration. And only then we can really tell, yeah, we're controlling the conductivity on the semiconductor, because we, by setting given doping level, we set what is the charge carrier concentration, and we want to be independent of the temperature. So that should be our goal. And this is also what is then important. I link it, as you saw in the introduction when I listed the topics of this lecture. I'm linking it with the operating temperature, the minimum and the maximum temperature, because one of the things I want to look at is whether we keep still control at certain operating temperature of interest over the conductivity of our semiconductor. So coming back to here, it's something very trivial, but step by step we just see that it all makes sense, that at some point these are the important things to notice when it comes to temperature and conductivity control. So for n-type semiconductor, we were mainly interested in the charge carrier concentration of electrons and holes next to the very high doping concentration that is added to the silicon that adds electrons, then holes become minority charge carriers. And with analogy, we have the p-type semiconductor with the acceptor doping. It's so high that we have a very large number of added holes in the semiconductor, and then the certain number of free electrons available for conduction, it's so small that it becomes negligible for, let's say, mostly. Sometimes we have to think about it, but when it comes to conductivity, it will be negligible. And what happens else in the energy band model? What you can see that in addition to the conduction band and the conduction energy, the bottom of the conduction band, and the valence energy, which is the top of the valence band, we have those two energy levels, the donor level energy in the n-type semiconductor and the acceptor level in the p-type semiconductor. And this is so very close to the respective bands that you will see in one of the slides. I have tables where the energy is listed for the dopants, how much energy we need to give to the charge carrier so that actually it moves to the valence or to the conduction band, that at a very low temperatures already the doping, it's working. So this is related to the freeze-out temperature. We go out of the freeze-out and these dopant charge carriers are available for conduction. And here I put in a question. What is the charge carrier concentration if donor and acceptor atoms concentration is identical? So if ND and AA, so donor and acceptor levels are identical, what happens in that case? So let's leave it open for a moment, probably up to this slide. We have this charge neutrality condition that is always fulfilled. So the concentration of intrinsic concentration of electrons and holes plus the concentration due to acceptor and dopant atom, it has to be equal. So this so let's say every ionized atom will have a corresponding free electron or free hole. So the total, in total, we have charge neutrality, however we dope with p or n-type semiconductors. So already we know from the question we can mix the doping. We can both add n-type and p-type dopant atoms in the same volume of semiconductor. And here we have the situation where we have and donor and acceptor at the same time. So we have this donor and acceptor energy levels added to the semiconductor. And what happens here is maybe you can already easily guess that because of this charge neutrality, if we have added electrons and holes, they will recombine with each other, and basically we stay with something that looks like intrinsic semiconductor. It's just we can never exactly balance it, but there are some regions where we have a starting material which is p-type, and we want to have it more n-type, then we need to add more charge carrier concentration in order to still control the conductivity. So understanding doping, it's maybe a new word in the vocabulary for some of you. So it's really just related to the semiconductor. And now we're coming back to the typical doping concentration. So as I said, typical range will be 10 to the power of 13 or to 18. And that means that if we have 10 to the power of 22 atoms in silicon, we will have one dopant atom per 10 to the power of 4 to 10 to the power of 9 atoms of silicon. So really quite a significant relation still, but it does make a difference in the conductivity. And what defines the minimum doping concentration and the maximum doping concentrations? It's what we cover with the next slides. So let's go back to the plot that we already know. And for silicon at room temperature, we have the charge carrier concentration that it's approximately at the level of the green line. So if we would like to control the conductivity for silicon, at the room temperature, we need to add charge carrier concentration that it's much higher than that. So that's already one reason why we need to define this minimum doping concentration, so the intrinsic charge carrier concentration. And we can see also that from this plot that the same charge carrier concentrations, the same dopant level concentrations, they would not work for germanium or for gallium arsenide, because we just need completely different levels, because our reference point here is, let's say, our target operating temperature is room temperature, so that's our reference how we want to dope the semiconductor. But in addition, we have defects and impurities at the material, which behave something like a bit like doping. So if there is some imperfection in the crystal, it will facilitate recombination. It will be additional center, and we need to come with doping above this level of impurities. So one thing that is important in the production of semiconductor that we will be talking quite a lot also in the future is the quality of the crystal. And if we would have some very poor quality crystal, then it would, so actually, maybe I will jump ahead and talk a little bit about the history, just one mention. So for a very long time, people thought that silicon is a metal because it was not possible to purify it straight early in the technology of the silicon, so that we can see that it's semiconductor and there is this temperature dependence of the charge carrier concentration. But there were so many impurities that it just looked like it's a relatively good conductivity conductor. And only later, so some already decades ago, now we can do that very well. People learned also how to purify it very well, so that we can, by cooling down, we can see that actually the conductivity is changing and reducing. So here is the importance of the material defects and impurities, and the number of impurities and defects per cubic centimeter has to be much, much lower than the dopant level that is of interest. And the other topic is actually so accurately controlling the dopant atoms itself, the concentration, and distributing it equally in the volume of the material, or in the certain maybe part of the material, so that we can tell that we can control it with such a low concentration. So minimum doping concentration, it's quite tricky. Then the maximum doping concentration. So there are also some interesting topics about it, and one thing that I was already mentioning is this impurity scattering. So the more dopant atoms we have, the more positive or negative charged ions there will be in the semiconductor. And when there is free charge carrier moving in the semiconductor, it will be influenced by the Coulomb forces induced by this ionized atom. And if we have many of them, then the mobility will be degradation. And secondly, the band gap structure is changing when we add more and more dopant atoms. So what happens? At first, it's maybe something that we can nearly ignore, but when we reach the levels of 10 to the power of 18 and higher, then we have this distance between dopant atoms that is calculated for the 10 to the power of 18. So it's 10 nanometers. And 10 nanometers, that becomes already very close enough to the lattice constant, that everything also that we were talking about, the band, the energy bands, we are at the region that this becomes important. So if you remember the Pauli exclusion principle, so we cannot have two dopant atoms. The dopant atoms are already so close that the wave functions start overlapping, and two dopant atoms will have energy states for the charge carriers that would be identical, and they are within this overlapping of the wave function. So at that moment, we have also this band shifting of this discrete energy level for donor and acceptor. They become also so they have to split the energy levels, and effectively what happens, they are going to touch the valence or conduction band, and because of that, the effective band gap that we see in the end is narrowing. Or maybe there are also some cases that I don't cover. I'm not so much familiar with the topic, but maybe the band gap energy can also get wider. I'm not sure about that, but basically what happens is that the band gap energy can change when the dopant atom concentration gets very high. And finally, at some point, when we place the dopant atoms in silicon, we have to activate them. That means with the high temperature, we ensure that the covalent bonding between the atoms takes place. And at some point, we cannot find space in the crystal anymore for the dopant atoms because there are just so many that they won't be, so to say, integrated in the silicon structure. Here we have the doping and probability of finding an electron. That means the energy, Fermi energies. So for intrinsic semiconductor, we have just the first green part. That would be for the intrinsic. And when we add n-type doping or p-type doping, then we will have this component. So the Fermi energy is shifting. And what we can see, it depends for sure on the temperature, because the Fermi energy depends on the total charge carrier concentration, or the relation between the dopant atom and the intrinsic charge carrier concentration. And so doping type, doping concentration, and the temperature, because it's related to the intrinsic charge carrier concentration. So when we look on the band diagrams, in the intrinsic semiconductor, the Fermi level is nearly in the middle. We can assume it's in the middle of the between conduction and valence band. For the donors doped semiconductor, the Fermi level shifts up, and as the temperature increases, the Fermi level actually is going to be coming back towards the mid-gap, towards the n-type semiconductor. When we increase the temperature, will look more and more like the intrinsic semiconductor, because there are more charge carriers thermally generated, which will approach the concentration of the donors. So what happens is the Fermi level is decreasing. In case of acceptor, we will have the energy level, the Fermi energy closer to the valence band because of this additional dopant atoms. So it's more probable to find a hole than electron, in other words. And when we increase the temperature, then the Fermi energy also is moving towards the intrinsic. And we can visualize it with the probability function. So in case of intrinsic semiconductor, it's the Fermi energy is in the middle, so it's equally probable in the middle to find the hole or electron. That means we have the same number of holes and electrons, because in the middle we don't really find anything. In case of the n-type semiconductor, what we have is it's more probable to find electrons. So this function shifts to, let's say, to the right, upwards. And in this case of p-type semiconductor, it will be at the Fermi energy. It's again the probability of half that we find an electron or hole, and because we have higher concentration of holes, then this energy level has to shift downwards towards the valence band. This is a graphical representation of what happens with the charge carrier concentration as a function of temperature. I think that we already had a similar plot, similar visualization. But now that we talk specifically about dopants, we can analyze once again what happens. So at very low temperatures, close to 0 K, nothing happens, because the charge carrier concentration, that it's due to thermal generation of silicon holes and electrons, it doesn't give any charge carriers. And we need certain temperature to reach the thermal generation just of the dopant atoms from the acceptor and the donor level. Then for a long time nothing happens, and with the charge carrier concentration, nothing happens in the log scale. It's a logarithmic scale, because the intrinsic level is so much lower that no matter if we add 10 more, it will not make difference next to 1 million, something like that. So we call this region saturation, and this is between the two temperatures shown with the dotted line. It would be ideally our operating temperature, where we say, okay, in this temperature range, I'm controlling the conductivity, and I know what it is. And no matter how the temperature changes, still in the log scale, I can estimate what the conductivity is. But as we reach very high temperatures, then this intrinsic charge carrier concentration starts to dominate, and then we can run out of control. So this is the region related to the plot with silicon or germanium or gallium arsenide that we were already looking at probably 3 other times before. So what is the ionization energy to go out of the freeze-out, to give us the idea what we need as thermal energy to get out of the freeze-out? So for silicon and germanium as a reference, we have the band gap energies, which is 1.1 electron volts and 0.67 respectively. And then this ionization energy for the different dopant atoms will be different whether we are in germanium or in silicon, just because they are different materials, even though the silicon structure in both cases it's 4 covalent bondings formed with the neighboring atoms. And so this is for reference. You can see that it's much, much smaller than the band gap. So if we have the forbidden energy band, which is 1.1 for silicon, then this donor level or acceptor level in silicon, it's really very close to the conduction or valence band in comparison. The topic that I find really interesting is to see like how much we can push the material to go, despite those limits that we have learned about, to go to low temperature or to high temperature. And there are, when we do, let's say, literature studies, we find really amazing things. So speaking about extreme temperature, we can talk about either very low, even cryogenic, or very high temperatures. So I would like to stop for a moment as a conclusion of this part on those two extreme ranges. So why are we interested at all in cryogenic? This is, for example, because we have some detector that works very well when we don't have intrinsic charge carrier generation, or maybe some other phenomena that is thermally related phenomena, because the detector doesn't have to be semiconductor. But there is electronics very close to the detector, and we want to cool down the electronics, the readout as well. So that's the usually most of the time that I find is the motivation. We can have some special other low temperature applications. So what happens as we decrease the temperature, we have the freeze out. We know that already. So one thing that happens, we have less charge carriers. So that increases the series resistance. That's for devices is very important, that when we see we have certain characteristics of the semiconductor device, then series resistance can make a big influence. And that's actually a minus. Another thing that happens is that we have a reduced phonon scattering. So the vibration of the lattice is lower because of the lower temperature. So because of that, we have a higher mobility and better transconductance. And this is what we can see here on those plots. Maybe after we discuss the topic of MOSFET, you will be able to even appreciate even more. What happens here is that the temperature increases with the color. So more yellow, it's a higher temperature, and we can see temperature starting with 4 Kelvin. In fact, we can see even sub-Kelvin operation of semiconductor. And actually what we can see here is that what we have here is the current of the transistor as a function of gate to source voltage. And gate to source voltage is what we control when we want to switch on or off the switch. And what we would like to do is that when we switch on, or when we change the switch between on and off condition, that the current changes by orders of magnitude, because that gives us the quality of the switch. And what we can see here is that with the purple line, it's much steeper. So that means with a smaller change of the gate to source control voltage, the current changes by more orders of magnitude. So we can see it's actually this works better at low temperatures. And what somebody might ask, so how does it still work at low temperature where we go? So this is 4 Kelvin. And that's about the level of freeze out. And I'm talking here about even sub-Kelvin operation. And then we have this cross-section of MOSFET transistor, where normally we would like to have charge carriers that actually go between the drain and source and provide some current, and they come from the thermal generation. But if we don't have it, it's enough at very low temperatures to increase just the fact that we increase the voltage at drain to source, then we will have enough to kick one charge carrier. It will already interact with other atoms, and just by the impact of the charge carrier moving, it will give energy to another atom to ionize it. And like that, because of this effect, we have charge carriers actually available for conduction without the thermal energy, but through the electric energy and the charge carrier movement. The other extreme, maximum operating temperature. So we have the thermal generation of doped semiconductor, and very soon, as we increase the temperature, it's overwriting the doping concentration. What I would like to show here is a simple calculation of how we can calculate the maximum operating temperature. So we start with the expression that you use to calculate the intrinsic charge carrier concentration. And what is hidden there is the density of states for electrons and holes. We have the energy band gap and the temperature. So when we transform this expression, this formula, to have the temperature on the left-hand side, we call it the maximum temperature, will be equal to, so let's say the Ni we replace with the doping level concentration that we have, and that will be the level that we don't want the intrinsic concentration to exceed. So that will be the limit for our temperature, and so this way from here we replace Ni with Nd, the doping concentration. We transform to have temperature on the left-hand side, and this way we calculate the temperature that it's maximum in order to still keep control by dopant carrier available for conduction. And like that, we can calculate the maximum operating temperature, knowing that the intrinsic charge carrier concentration at 300 Kelvin is intrinsic carrier concentrations is like that. If we take this as the, well, let's say the doping concentration actually is not included here, because for silicon the doping concentration we said it's quite a bit higher. So it's still the estimation of the maximum operating temperature is 150 Celsius for silicon. So this is concentration at room temperature, and at 150 we will have different concentration. Then for germanium it's much lower because of the lower energy gap, 90 degrees, and for gallium arsenide 300 Celsius degrees. This is something that it's not necessary that we have to be limited by that, and I would like to show some more examples. So when we want to push our semiconductor to ultra high temperatures, typically we will say that, okay, we want to use a gallium arsenide or silicon carbide. So for silicon carbide we can reach up to 750 Celsius, or gallium nitride or diamond. But some examples from silicon. So what are the limitations? We can actually reach 250 degrees operation, but we need to have for sure much higher doping than, so very high doping levels. And there are some limitations related to the leakage currents that become, so we don't have this conductivity control so well as at lower room temperatures, but still the fact is that the devices can still operate, and we will have, for example, 250 Celsius for silicon or insulator, because this stops to some extent the issues that occur because of latch-up or leakage currents. Another issue is reliability because of the electromigration. That means the metals, tungsten and copper, they don't stay where we wanted them to be, so there is migration when the current is flowing. And 200 degrees was shown in some application to be the maximum. And then there are some other things that maybe those numbers that I'm giving here are rather single examples, because in the big scale fabrication we would have challenges of time dependent dielectric breakdown, bias temperature instability. These are typical reliability topics that after the operation over a certain time, the devices don't work as initially when tested right at the start. Okay, so a short summary of doping. It changes performance of semiconductor. It is, for example, what we have to look at is the temperature dependence of the conduction, and we would like to be independent of the temperature. We have the N-type and P-type doping, and also this defines the majority and the minority carriers of semiconductor. So far about doping, and with doping, maybe the final question, what happens? The conductivity is better under all operating conditions, or the number of charge carriers can be controlled, conductivity stays constant over a certain temperature range, mobility is getting higher. So I think that after this part, it should be easy to answer.
You're the signal in my static hum, a perfect match we've overcome. Wires cross but we still run, sparks fly.